Hey everybody, Thrasher here. This is a new set of videos all about energy and terms associated with it. I know there's a lot listed here, but either these are quick definitions or these will actually be kind of expanded upon later on in future videos. So we're just kind of getting our feet wet with some of these terms. The first thing I want to talk about is energy and how it's a term that is very vague, even in a physics context. The official definition for energy, while you may have heard it before, depending on past science classes or experiences you've had, while one exists, it's very broad. And that's because energy takes very many different forms. To be honest, I recommend for this class, since I will never directly ask you to define energy, the AP test is never simply going to ask, what is the definition of energy? That's not going to happen. So in terms of something to work with, that's going to help you get through things, let's just think of energy as it's the ability for you or any object to do something, right? That's very broad because, again, energy takes many forms. Think of like walking. Walking requires energy, okay? Think of like forming molecular bonds. Oh my gosh, that's a whole other type of energy. But forming molecular bonds, that's an action. That's a verb. Any kind of action or verb you can think of, well, it probably requires an amount of energy. There's also some examples like falling. Oh, if you are falling maybe because of Earth's gravity, that's something, right? That's an action, that's an activity in a way that also requires energy. So let's just stick with that. It is not official, okay, but it's a good way to keep energy in mind as we go over some more official things. So energy, it's just the ability to do something, okay? Now, let's go into another term known as work, and this is going to be a very important physics word for the next couple of class periods in my own class, the next couple of videos, okay? It has to do with forces, and it has to do with distance, things that we've already learned. Here's what it says. When an object experiences a force over some distance, so there's force, there's distance, we say that work was done on that object. Okay, it's a new definition. So here I have this diagram right here. I have this person. They are applying a force on this box. Imagine this box is moving. It's sliding to the right. Well, there is work being done because there is a force applied. It travels some distance. So I'd be like, oh, okay, this work here is equal to the force multiplied by distance. That, in fact, is our equation right here. It's just the two things being multiplied. That's pretty easy, except there's maybe a little bit of a caveat. Do you notice this little symbol, these two little parallel lines? Well, that means the official definition of work, kind of to make sure we're all in the same convention, we're all talking about the same thing, we're always going to use the force and the distance that's parallel to one another. Force and distance that's parallel. What do I mean by that? And that's why there's these two parallel lines. That in geometry and math, that represents parallel. Well, look back down at my diagram. The displacement or the distance in this blue, well, that's horizontal, right? The force is also horizontal. Those two things are parallel, so you would just multiply those two forces together. But let's say instead this person was applying a force that was maybe slightly upwards like this. Okay? They're still making the box move. It's still moving across to the right, so it still travels a distance. How would I calculate the force in that example? Well, I still use this equation, but so we're all on the same page, we're going to use the parallel component. So we are using components in this section, in this new energy section, but for a different reason. If we knew maybe the angle that this pushing force was, let's call that theta, we would want to find Fx. And in this example, Fx, this piece that is parallel to the displacement, that would be, if you remember your trigonometry, F times the cosine of theta. So if I was going to calculate the work for this force that's acting at an angle, work is equal to force parallel times displacement. In this example, that would be F cosine theta times d. So still a little bit of trig, but you're actually going to find in this unit, trig is getting less and less important. We're not going to be doing it as much. But technically, when you're finding the work done by a force, you are using the component of that force that is parallel in the same direction as that displacement, okay? The next big idea, so here's one big idea about work. There's an equation. The other big idea is that when work is done on an object, its energy changes. Remember what we said in just that last slide. While we're not going to look at an official definition of energy, it's not super important, this idea is crucial. When there is work being done on an object, and sometimes the verbiage is a little weird. You might say work is done on an object. this person is pushing the box, work is done on the box. Well, think about it. If that box was at rest, all of a sudden, by pushing on it, it starts moving. Oh, now it's doing something. It seemed to have gained energy. So doing work caused the energy of that box to change. If there was friction, imagine there was like a frictional force acting on this box. We know that friction opposes motion. Okay, maybe imagine a slightly different scenario of a ball rolling and slowing down. Oh, friction causes that ball to slow down. Friction can do work on the object. That could maybe make it lose energy. So it's another equation, but it's also a concept. Work causes a change in energy for an object. Maybe it can now do something, or maybe it can now do less of some activity. Okay? Now, the other thing about work, and there's a lot of kind of nuances about work, but don't worry. Okay, there'll be more elaborations on this on future videos, and of course more practice with problems. Work is a scalar. So we're not going to worry about positives and negatives for direction. When you're calculating work, you don't have to think like, okay, let's say right is the positive direction, so work to the right is positive. We're not going to do that. So direction is not going to be super important. However, work can be positive or negative, and that's going to be to indicate two things. Okay? If the force and the distance are in the same direction, we'll say that work is positive. And we do that because if the work is positive, that's like the object is gaining energy. Let's go back to this example. I'm pushing on the box. Well, that force was in the same direction as the displacement, whether it was this version or this version. That's parallel in the same direction. That's a positive force or positive work by this convention. And the box gained energy. But look down here at this second bullet point. The frictional force is acting in the opposite direction. So when that box is moving and there's friction, those are in opposite directions. We're going to say that the work is negative, and that makes sense based on this idea. Because you could pretty easily imagine, I bet, that friction removes energy. It takes away, right? It's fighting you. So the work being done by frictional force, its force multiplied by this displacement, they're in opposite directions. We're going to use a negative work to indicate that. And by the way, that makes sense also trigonometrically, because if my angle was negative 180 degrees, that would be -1. You get a negative work. But that means it's losing energy. I know I'm going quick and this is a lot to take in, but you're going to become pros at this because we'll be spending a lot of time. Okay? Now, how is work measured? It's a force multiplied by a displacement, so that's a Newton multiplied by a meter, a Newton meter. Work is measured in Newton meters. You could write that on future homeworks or exams, but it's also given a special name. A Newton meter, that's known as a joule, named for a scientist, mid-17th century, a scientist joule. So use uppercase letter J for joules. You could just use that. So how much work is on the fridge? If I do some calculations, maybe I find it's 18 Newton meters, or you could just call that 18 joules, okay? Not only can I look at the work done by a specific force, I could look at the overall work, the net work, done by the overall net force. So maybe in this scenario, if I want to look at the overall work done, maybe I do something like, all right, let's see, I got the sum of the forces. There's this pushing force F minus friction, that equals ma. Well, this is the total amount of forces. The overall work, the net work, that's equal to the net force multiplied by displacement. So you could almost zoom in to one force, find the work done by it, or zoom out and look at the overall amount of work. And the problem will make that clear if it's either saying find the net, the total work, or the work done by one particular force. Okay? Let's keep going. So we learned about work. Let's learn about something called the work energy theorem. Using our equation for work and what we know about overall forces and constant acceleration, we can derive an equation that introduces something known as kinetic energy. In fact, kinetic energy, I bet it's a term that a lot of you are familiar with. Now, this derivation, I don't want to spend time right now in this video because this video is going to be long enough. My next slide will show the derivation. You could hit pause if you want to look over it. I'm never going to require that you define it. but this derivation creates something known as the work-energy theorem. So here's that derivation all by itself. If you want to hit pause, go ahead. But I'm going to focus on this result right here. The work done by net forces on an object. Okay, so if we look at all the forces acting on an object, if we look at the net work that's being done, that causes an object to have a equation that looks kind of like this. This equation right here. The work done by looking at the overall forces, you get this thing, 1/2 mv squared minus 1/2 mv naught squared. Remember what we said in the past couple of slides? Work causes a change in energy. And if you notice, I have kind of a final velocity here and an initial velocity. I have a change going on. This term, which maybe you might recognize as something called kinetic energy, this is where kinetic energy comes from. It doesn't come from some random scientist just being like, I want to create a new term. I'm just going to go ahead and multiply 1/2 times mass times velocity and call that a day. It comes from a derivation of looking at forces and the work done by those forces. So this term pops up, and this is actually a very fundamental physics equation. What does it say? It says that the net work that's done on an object causes a change in something. It's a change that's affecting the mass, and it's affecting the velocity. Because these two terms pop up, kind of a final version and an initial version, scientists look at this like, man, this is pretty fundamental. An overall amount of work causes a change in these two terms. And therefore, that's why this term, known as kinetic energy, is given importance. Because when there's an overall amount of work done on that object, it experiences a change in kinetic energy. So that's what the work-energy theorem says. It's an equation. It says the net work on an object, and that would be, the net force multiplied by the displacement. It causes the kinetic energy multiplied by mass multiplied by 1/2 to change by some amount. Okay. Why do they call it kinetic energy? Why is this term given the phrase kinetic? Because it has velocity in it. And velocity means motion. The word kinetic means motion. So not only do we have this overall equation here, this thing called the work-energy theorem, but also this term is pretty important. And this term is known as kinetic energy. So that kind of becomes visible now by doing that derivation on the last slide. So kinetic energy, it's a type of energy, and it has to do with an object's motion. If something is moving, it has velocity, of course, and therefore it has kinetic energy. Oh, and that's a type of energy. Therefore, it's also measured in joules. All energy, just like work, okay, these two units have to agree with each other. All energy is measured in joules, kind of like how all forces are measured in newtons. And this is a type of energy associated with the movement of objects. And how can I cause a change in kinetic energy? I apply overall work. I apply a net force for a distance. So, okay, oh my gosh, that was a lot, I know. We kind of went over the vague definition of energy. Then we talked about work, forces, and distances, but also changes in energy. And then we looked at this work-energy theorem. That's a lot, I know, but don't worry. This is our focus for the next few classes if you're in my class, and we'll see more examples of this in detail as you proceed in future videos. But this is a broad overview of energy, work, and also where this kinetic energy comes from. Okay, that was a lot. I'm stopping the video now. Thanks a lot for watching.